So in this video we'll solve the remaining sums of chapter 8 electrostatics. 125 small liquid drops each carrying a charge of 0.5 microcoulomb and each of diameter 0.1 meter forms a bigger drop, and we need to calculate the potential at the surface of a bigger drop. So solution: a bigger drop is formed. Let's take the radius of a bigger drop as capital R of small droplets each having a charge of 0.5 microcoulomb, and we need to find out the potential at the surface of this bigger drop. So the formula for potential is V equal to 1 upon 4 pi epsilon naught Q upon R. So this is the total charge of the bigger drop. Now the total charge of the bigger drop will be the sum of all the charges of the smaller drop, that is 125 into charge on one drop, that is 0.5 into 10 raised to minus 6 coulomb. So the total charge on the bigger drop will be 62.5 micro coulomb, and we also need to find out the radius of the bigger drop. So we can say that 125 into 4 by 3 pi r cube, that is the volume of one small drop, is equal to the volume of the bigger drop. From here we can say that capital R cube is 125 times the small r cube, so which implies R will be equal to 5r, and the diameter of the smaller droplet is given as 0.1 meter, so small r will be 0.05 meter. So this r will become 5 into 0.05, which comes out to be 0.25 meter. Now let's calculate the potential. So V will be equal to 1 upon 4 pi epsilon naught capital Q, that is 62.5 into 10 raised to minus 6 divided by 0.25, and 1 upon 4 pi epsilon naught is given as 9 into 10 raised to 9. So calculating this, we get potential equal to 22.5 into 10 raised to 6 volts. I hope you understood this sum. Let's look at the next one. The dipole moment of water molecule is 6.3 into 10 raised to minus 30 coulomb meter. A sample of water contains 10 raised to 21 molecules whose dipole moments are all oriented in an electric field of strength 2.5 into 10 raised to 5 Newton per coulomb. We need to calculate the work to be done to rotate the dipole from the initial orientation theta 1, that is at 0 degree, to theta 2, which is at 90 degree. So solution: the work done to rotate a dipole in an electric field is given by Pe cos of theta 1, that is the initial angle of the dipole, minus cos of theta 2, that is the final angle of the dipole. So this is the work done to rotate one dipole, but we have 10 raised to 21 molecules of water. So to rotate 10 raised to 21 molecules of water under an electric field, the work done will be n times Pe cos theta 1 minus theta 2, where n is 10 raised to 21. So the work done will be 10 raised to 21 into the dipole moment is given by 6.3 into 10 raised to minus 30 coulomb meter into the electric field strength is 2.5 into 10 raised to 5 into cos of theta 1. Theta 1 is 0 degree, so cos of 0 degree minus cos of theta 2, that is cos of 90 degree. So cos of 90 will become 0 and cos of 0 will become 1. So the work done will come out to be 15.75 into 10 raised to minus 4 joule. So this much amount of work is to be done to rotate all the 10 raised to 21 molecules of water from 0 degree to 90 degree. Let's look at the next one. A charge 6 microcoulomb is placed at the origin and another charge minus 5 microcoulomb is placed on the y-axis at a position A 6 meter above. So if this is y-axis, this is x-axis, one charge is placed at the origin of 6 microcoulomb and another charge is placed at a distance of 6 meter, that is of charge minus 5 microcoulomb. We need to calculate the total electric potential at a point P whose coordinates are 8 comma 0, that is at a distance of 8 meters on the x-axis. So this distance is 8 meter. So the total potential will be sum of the potential of this charge and sum of the potential of discharge. So we know the distance of discharge with point P. We need to calculate the distance of discharge with point P. So this forms a right angle triangle. So from Pythagoras theorem we get 6 square plus 8 square, that is 10 meters. So let's calculate the potential. So potential due to 6 microcoulomb will be 1 upon 4 pi epsilon naught 6 into 10 raised to minus 6 divided by 8 plus 1 upon 4 pi epsilon naught minus 5 into 10 raised to minus 6 divided by 10. And solving this, taking 1 upon 4 pi epsilon naught outside, we get, and 10 raised to minus 6 also, 6 by 8 minus 5 by 10. So solving this, we get the potential to be 2.25 into 10 raised to 3 volts. So this is the potential at point P due to these two charges. Secondly, we need to find out the work done to bring a proton from infinity to a point P, and what will be the significance of a negative charge. So since these two charges creates a total potential of 2.25 into 10 raised to 3 volts, that is the potential is positive. That means if we are bringing a proton, we have to do work against this potential. Okay, so if we are bringing a proton from infinity to point P where the potential is positive, that means we have to do a work against the potential. So work done is given by V into Q, but with a negative sign, which signifies that we are doing work against the potential. Now minus of 2.25 into 10 raised to 3 into charge of proton. Charge of proton is same as charge of electron, that is 1.6 into 10 raised to minus 19 coulomb. So solving this, we get work W to be 3.6 into 10 raised to minus 16 joules. So this much amount of work we have to do against the potential in order to bring a proton at a point P from infinity. I hope you understood this sum. Let's look at the next sum. In a parallel plate capacitor with air between the plates, each plate has a area of 6 into 10 raised to minus 3 meter square and the separation between the plate is 2 millimeter. So solution, area is given to us as 6 into 10 raised to minus 3 meter square and the distance between the plate is 2 millimeter, which can be written as 2 into 10 raised to minus 3 meters. We need to calculate the capacitance of the capacitor. Since there is no dielectric present, the capacitance can be written as C equal to epsilon naught A by D. Epsilon naught is 8.85 into 10 raised to minus 12 into area is 6 into 10 raised to minus 3 divided by D, that is 2 into 10 raised to minus 3. Solving this, we get the capacitance to be 26.55 into 10 raised to minus 12 farad, which can be written as 26.55 picofarad. Now secondly, they have asked us that if a capacitor is connected to an 100-volt supply, what will be the charge on each plate. So we know the formula for charge is given by Q equal to Vc, where V is the potential difference applied. So V is given to us as 100 volt into the capacitance that we got 26.55 into 10 raised to minus 12. So we get the charge to be 2.655 into 10 raised to minus 9 coulomb, which can be written as 2.655 nano coulomb. And lastly, they have asked us how would charge on the plate be affected if a 2 millimeter thick mica sheet of dielectric K equal to 6 is inserted between the plates while the voltage supply remains the same. So when a dielectric is placed, we can say that the charge will be Q dash, which is equal to C dash V dash. But since the potential difference applied is remains the same, so V dash is equal to V. Now Q dash will be C dash, that is the capacitance when dielectric is placed is given as C dash equal to K times C. So which we can write K times C into V. Now CV is our old charge Q. So Q dash can be written as K times Q. So K is given to us as 6. So this will become 6 times the old charge, that is 2.655 nanocoulomb. So the new charge we get Q dash equal to 15.93 nanocoulomb. I hope you understood this sum. Let's look at the last sum of this chapter. So we need to find out the equivalence capacitance between P and Q given the area of each plate is A and the separation distance between plates is D. So in the first case, three capacitors are connected in series with the dielectric between them as 1, 2 and 3, and the distance between the plate as d by 3, d by 3 and d by 3. So we know general formula for capacitance is C equal to K epsilon naught A by D. So here the capacitance are connected in series. So 1 by Cs will be 1 by C1 plus 1 by C2 plus 1 by C3. So this will be 1 by C1 is K1 times, let's take this as K1, K2 and K3. K1 times epsilon naught A, since the area of all the plates are same, by D. Now D is D by 3. So if this goes up, this will be D by 3. Similarly for C2, this will be D by 3 K2 times epsilon naught A, and for C3 it will be D by 3 K3 times epsilon naught A. So 1 by Cs will be equal to D by 3 epsilon naught A into 1 by K1 plus 1 by K2 plus 1 by K3. So the values of K1, K2 and K3 are actually 1, 3 and 6. So this will be 1 by 1 plus 1 by 3 plus 1 by 6, and outside was D3 epsilon naught A. So solving this we get D by 3 epsilon naught A into 9 by, which implies we get 1 by Cs equal to D upon 2 epsilon naught A, which implies the equivalence capacitance Cs is 2 epsilon naught A by D. Now let's see the second case. So in the second case, these two capacitors are in series with the equivalence capacitance with this capacitor in parallel. So first of all, let's calculate the equivalence capacitor for these two capacitors. So 1 by Cs will be equal to 1 by K2 epsilon naught. Now here area is A by 2. So A by 2 upon D. Now D will go up. So D by 2 plus, for second it is D by 2 K3 epsilon naught A by 2. So 2 gets cancelled, and we have here also. So 1 by Cs is equal to D by epsilon naught A 1 by K2 plus 1 by K3. So solving this we get 1 by Cs equal to D by epsilon naught A. K2 is 1 by 3 and 1 by 6, which implies from here we get Cs equal to 2 epsilon naught A by D. Now this value is in parallel with another capacitor with dielectric K1. So the total capacitance C is equal to C equivalent Cs plus another capacitor C, which is 2 epsilon naught A by D plus, now this capacitor has dielectric K1 and epsilon naught area is A by 2 with distance between the plate D, and K1 is given to us as 4. So 4 times A by 2, so this 2 gets cancelled. We have 2 epsilon naught A by D and 2 epsilon naught A by D. So this will be 4 epsilon naught A by D. So this is the equivalent capacitor for this. So C equivalent, here we get 4 epsilon naught A by D. I hope you understood all the sums that we did today for this chapter. So thank you for watching this video.